today we are going to move to another subtopic or chapter, which is our lecture 4, called as Principles of Parallel Algorithm Design. So this chapter actually will discuss about how we want to choose the best approach to design the algorithm. In this case, is parallel algorithm. So, however, if you look at the number of slide, only 41, madam only want to teach until slide 20. So, kita bagi dua lah, tak nak banyak sangat. Alright, so what we are going to cover in this lecture. Okay, so let's look at the scope of this chapter. Introduction to parallel algorithm. So what is meant by task and decomposition? What are the processes and mapping, processes versus processors. Okay. And then the next one, we will learn about decomposition techniques. So in parallel, we always deal with break up the large tasks into smaller tasks. So we need a decomposition technique. Decomposition ni macam break up lah. Break up the large task into smaller tasks. Okay, and then there are 4 types of decomposition technique. Recursive. Actually recursive ada 2 kat situ kan. Ada satu lagi yang lain. And then exploratory and also hybrid. Nanti kita tengok apa benda satu lagi selain recursive ni. Okay, and then another one is characteristics of task and interaction, which are task generation, the granularity and context, characteristics of task interaction, and what else? Mapping techniques and load balancing, methods for minimizing interaction overheads, and last one is parallel algorithm design model. However, for today, we are going to touch only this one. Introduction to parallel algorithm, anti-processors versus processors. Okay, so let's start. Alright, so let's look at the preliminaries. Okay, what is meant by decomposition, task and dependency graph. So, okay. So the first step in developing a parallel algorithm. So the first step is what you need to do is decompose. Decompose the problem, the big problem, into several tasks that can be executed concurrently lah. So we need to identify whether our problem can be decomposed or break up into tasks and can be executed concurrently or not. Okay, so a given problem may be decomposed into tasks in many ways. Maksudnya there are lots of ways, various ways. Okay, to decompose the task. So as we look at the slide, the previous slide, there are 4 types of techniques that we can decompose our problem into tasks. Okay, so the task may be of same, different, or even intermediate sizes. Task, it can be any kind of size. Okay, and then a decomposition can be illustrated in the form of a directed graph with nodes. So when we want to make a decomposition technique, guys, okay, so we can illustrate, we can plan or draft our process of decomposition ni by using a directed graph. A directed graph with nodes lah. The circle shape tu with the edge, okay, anak panah corresponding to task and edges. Okay. So the node is represent the task and the directed, the straight line, okay, the directed line is also known as edges. So indicating that the result of one task is required for processing the next. So by using the graph, so we can see that, oh, task 1 required or task 2 required the input or output from the task number 1. Task 3 depend on task number 4, something like that. So based on the directed graph. So that graph actually is called as task dependency graph. So you need to remember this. Task dependency graph ni consists of node. Node yang represent the task and also the edges, the result of the next process lah, where to direct the task to go after the first process is being executed. Okay, so next one. Okay. Alright, so let's look at the example. This is an example of multiplying a dense matrix with a vector. A is the matrix, okay, the task from task 1 until task n, and B is our data, Y is the output lah. Okay, so as you can see there, the computation of each element of output vector Y is independent of other element. Y tu the independent. Dia tak depend on A or B. Based on this, a dense matrix vector product can be decomposed into n tasks because of Y is independent. So then, we can decompose this process, okay, into several, or in this case, n tasks. We don't know how many tasks that we can decompose it. So the figure highlight the portion of the matrix and the vector accessed by task number 1. If you can see here, task number 1, okay, has n tasks that can be decomposed or break up. Okay, and then will be multiplied by B and we'll get the Y output. Okay, so observations. While tasks share data, okay, share data, task A, share data with B with the vector B, they do not have any control dependency. So for example, no task need to wait for the partial completion of any other. So dia tak ada dependency to anything. So tak perlu wait. Okay, no need to wait for the partial completion. Tak perlu, no need to wait for other tasks to be completed. All tasks are the same size in terms of number of operation. So maksudnya all these tasks is being decomposed into same size in terms of number of operation. So they can do the decomposition technique. Okay. So the question asks, is this the maximum number of tasks we could decompose the problem? So how we want to know the maximum number of tasks that we can decompose? So we need to do something lah. We need to analyze our problem. How to analyze it? We need to use the graph that we have discussed in previous slide. Okay. So let's look at another example. This is database query processing. So this is the SQL query. Okay, model equals to civic and year equals to 2001 and color either green or white. So this is the table. So we want to find this output. So dia nak analyze this kind of task tu. So this is where the problem is being analysed lah. We want to display this kind of output civic year 2001 and either green or white from this table. So let's look at the next slide. Okay, so one way that we can do the decomposition task. So dia kata the execution of the query can be divided into sub-tasks in various ways, many ways. So each task can be thought as generating an intermediate tables of entry that satisfy a particular clause. So if you remember the previous one, the SQL name, okay, so we need to find the output step by step. So we need to find the model of the car first and followed by the year of the car, and then we need to find the color, which is green and white. So this actually the SQL statement can be break up into several processes. So as you can see here, civic. Okay, so they find out that civics ni consists of many IDs, ID number and then do the next task or process, which is find the year, which is must be 2001, and the color must be either white or green. So these 4 tasks actually is being implemented or being executed in parallel because of what? Dia tak depend on each other kan. Civic je lah. 2000 tu semua tak ada depend on each other. So each of these can be run in parallel in one time. Okay. So next, they must find the next task, next level, they must find the car model must be Civic and year 2001. 1. So itu. So and then when it run the code, so okay, so we get only 2 car. 6734 and 4395. Okay, and same goes with the to find the color, either white or green. When they run these two code, white and green, okay, so they find, okay, there are 2, 4, 6 ID of car that have white and green color. So when they combine together, Civic and 2001 with white or green, actually the output is only one that match with the required SQL code. Okay, so decomposing the given query into a number of tasks. Edges in this graph note that the output of one task is needed to accomplish the next. If you notice, this is the graph. This is the node. Okay, and then the node has the edge that shows where to proceed. Okay, which node that need to be pointed. Okay, so this is one of the example of the graph. Okay. All right. So next one, another example. Okay, this is another way. Okay, the first one, it find the all the car model, year, color, white and green is being executed at once. Okay, then it's followed with find the white or green first. Okay, after it get the output of color, then followed by this one. Okay, and then please look at the age. After it finds civic, it goes to the last step. Okay, directly. Okay, so this is another option. So any developer or any programmer will have their own way to solve the parallel execution on getting the result. Okay, so an alternate decomposition of the given problem into subtasks along with their data dependency. So different task decomposition may lead to significant difference respect to their eventually parallel performance lah. So lain cara, lain algorithm will have different performance of in terms of time, in terms of speed and so on. So depends on the algorithm on how we want to write or to break up or to decompose the problem into several tasks. Okay, next. Okay. We move on to the next subtopic, which is granularity of task decomposition. We want to know the size. Okay, how large does the problem is being decomposed into smaller tasks. So what is meant by granularity, or it actually taken from the word granular, is used to describe something that is made up of multiple elements. Okay, so in this case, we have two size of granularity. So the number of tasks into which a problem is decomposed determines its granularity. So depends on the programmer itself on how many tasks that they will decompose. Okay, so decomposition happen when, okay, there are two situations here. If the decomposition into large number of tasks result means from one problem to many tasks, okay, it is called as fine grain. So it become finer because you have lots of smaller tasks to be executed. And then the opposition of fine grain is called as coarse grain. So coarse grain is actually a small number of tasks result in a coarse grain. Means if one problem and then you decompose into several tasks, but that task is not so many, so it is called as coarse grain. Okay, so a coarse grain counterpart to the dense metric vector product example. Each task in this example correspond to the computation of three elements of the result vector. Okay, so bear in mind there are two types of granularity. Either one problem being decomposed into large number of tasks, it is called as fine grain, or either one problem being decomposed in a smaller size of tasks, it is called as coarse grain. Okay, So ini this example lah, a smaller task, okay, being decomposed into small one task being decomposed into n tasks, right? Okay, next one. Degree of concurrency. So what is meant by degree of concurrency? The number of tasks. So degree is actually the number of tasks that can be executed in parallel. So we need to identify when we have break up the problem into several tasks, we need to know the degree of concurrency that we can execute or run at once. Okay, so that one is called as degree of concurrency. So since the number of tasks that can be executed in parallel may change over program execution, so it can be not be the same, cannot be the same. The number of tasks, the maximum degree of concurrency. So we have the maximum degree of concurrency between the tasks that we have decomposed is the maximum number of such tasks at any point during the execution. Let's say we have 5 levels of concurrency that execute the parallel task. So between the 5 level, we need to identify which level has the maximum number of tasks. So also known as maximum degree of concurrency. So inside the degree of concurrency, we also have another keyword here. We need to know whether the average degree of concurrency. Among the levels of concurrency that we have executed, we need to know between all the 5 levels of concurrency, what are the average degree. So the average degree actually is the average number of tasks that can be processed in parallel over the execution of the program, overall of the total works that we need to complete or execute. Okay, so assuming that each task in the database example takes identical processing time. So what is the average? So when we want to calculate the average degree of concurrency, we need to assume that all tasks has or takes identical processing time, have the same time of processing. So the degree of concurrency will increase as the decomposition becomes finer in granularity and vice versa, which means if you have more tasks to be decomposed, okay, so the degree of concurrency will increase, okay, so vice versa, okay. All right. So the next one we call as critical path length. So what is meant by this is a directed path in the task dependency graph represent a sequence of tasks that must be processed one after another. Okay. So let's say, please imagine you have the graph, you have the node. So we need to identify each of node too. Okay, so that one is the sequence of tasks that must be processed one after another. So we can find the critical path length from that graph, okay, or node. The longest such path determines the shortest time in which the program can be executed in the parallel. Okay, so the longest path is actually the critical path length. The length of the longest path is also known as critical path length, even though it is long, but actually is the shortest time to execute the task in parallel processing. Okay. So let's look at the example on how to find the critical path length, the maximum degree of concurrency, the average degree, and so on. So we have two graphs here. Okay, so let's look at the A graph. We have 7 tasks, right? So it represents with a task dependency graph, which has nodes and also the edges. Okay, so let's find the important points, okay, that we need to design the algorithm. So the first thing that you need to know is what is the critical path length in the graph. So how to identify the critical path length? So to calculate the critical path length, you need to know the definition of critical path length, which is the length of the longest path. So in this graph, guys, you need to find which one is the longest length of the path. Either here, task 1, task 4 to task 6 to task 7, or task 3 to task 6 or task 7, or task 2 to task 5 to task 7, or task 1 to task 5 or task 7. Okay, I want all of you to calculate. Okay, and then please specify or please respond to me which path that has the longest path, which is the critical path length of this case. Okay, which one? So please calculate first. Of course, we have the answer right now, which is 27, but from which path? Task 4 and task 3. Yes, task 4 ni and task 3 ni has the same length. Why same length? We need to total up. 10 plus 9 plus 8. So same with task 3, 10 plus 9 plus 8. So we get 19 plus 8, which is 27. How about task 2, 5 and 7? 10 plus 6 and plus 8 is 16 plus 8, 24, right? So this one, okay, this side is not longer enough. Okay, so when you find this kind of value, okay, so let's say you are given this kind of question, so you need to consider all the tasks, or sorry, all the path. Okay, so after you calculate all the path, you need to find out which one is the longest path. So the longest path actually is our critical path length. So how about the graph number B, guys? Which one is the most critical? Okay, we know the answer is 34, right? So which one? Whether task 4 and task 7? 17. Task 3, task 6, task 7? 10 plus 11 plus 7? 21 plus 7, which is 28. Task 2 plus task 5 plus task 6 plus task 7. How much? 16 plus 11, 27 plus 7, 34. Task 1 plus task 5 plus task 6 and plus task 7, which is similar to task 2 plus task 5, 6 and 7. So our critical path length either task 2, 5, 6, 7 or 1, 5, 6, 7. Am I right? Betul guys? Okay. So you all faham kan how to get the CPL? Okay, good. Okay, now we move on to the next one. Macam mana boleh dapat shortest parallel execution time equals to 30 times unit. Okay, sebab dia kata if each task takes 10 time units, right? What is the shortest parallel execution time for each decomposition? Why the answer is 30? Okay, so the answer is, okay, dia kata assume each task, semua ni, all these tasks represent takes 10 times unit. So if your critical path length just now required 3 nodes, right? So 3, 1, 10 plus 10 plus 10 to fulfill or to complete the length, the path. So required 30 times unit, right? Kan? Okay. How about this? Why 20? Between 20 or 40? 40 kan? Patutnya kan? Ya, betul. So, jawapan ni salah lah. So, should be 40. Okay, good. Alright, so next. Number 2. Maximum degree of concurrency. Kenapa 4, guys? Okay, so we need to know the definition of maximum degree of concurrency. So, maximum degree of concurrency is said that, mana tadi dia punya definition? Maximum number of such tasks at any point during execution. So, maximum number of tasks. So, okay, let's say graph A. We have 3 levels here. This is level 1, level 2 and level 3. Kat mana agak-agak yang kita dapat jawapan 4 tu, guys? Sini maximum degree. Maximum degree means at one time, at one level, it can execute 4 tasks in concurrency, in parallel. Okay, that's why the answer is 4. So same goes to graph B. It also can execute 4 tasks in parallel. So the maximum degree of concurrency is equals to 4. Okay, so we move on to the next one. Average degree of concurrency. So how to find the average degree of concurrency? Dalam slide ni dia dah explain kat you. Okay, alright. Number of tasks that can be processed in parallel over the execution of the program, the whole lah. So the way to find the average degree of concurrency, so actually you need to total up this first, all this node. So 10, 10, 10, 10, 9, 6 and 8, you will get 63. Okay, and then where to get the 27? From where? Actually from the CP L. So total amount of work for all nodes over CPL, you will get 2.33. So same goes with B. You total up all the nodes. You got 64 over 34 CPL. You will get 1.88 average degree of concurrency. Okay, boleh tak? Boleh Okay, kalau boleh, madam nak you all buat exercise kejap. Kita buat exercise. Start no. Okay. So I want everyone to find the critical path length, maximum degree of concurrency pula. Calculate the average degree of concurrency. Okay, madam bagi you all 5 minit cukup. Sekejap lagi kita discuss. Okey, dah siap? Okay, remember to find the critical path length, you need to consider all the tasks and path. Dah. Okay, so the answer for number one? 45. 45, betul okay, betul. Medium pun dapat 45. Okay, maximum degree of concurrency. 5, betul. Sebab dekat level 1 tu, dia boleh run sampai 5 task kan? Alright, good. Next one, average degree of concurrency. 2, okay. Y2, 90 over 45. Okay. Okay, kadang ada satu soalan tu dia kata please list the critical path length. The critical path. Dia tak cakap length tau. List the critical path. So, kalau soalan kata list the critical path, you need to list only, no need to total up. So, means you need to write either task 5 to task 6 to task 8 or task 9, or you can use 10 to 15 to 12 to 8. Okay, boleh yang tu kalau soalan minta critical path saja without the length. Alright, so semua dah pandai. So kita proceed to the next one. Alright, so limits on parallel performance. So actually the parallel performance also have its own limitation. So basically there are two limitations that being discussed in this slide. The first one is of course about the timing lah, and also the communication overhead. So it says that it will appear that the parallel time can be made arbitrarily small by making the decomposition finer in granularity. Sebab task is being decomposed into smaller size, right? So the parallel time can be made small lah. Okay, and then there is an inherent bound on how fine the granularity of a computation can be. So for example, in the case of multiplying a dense matrix with a vector just now, there can be no more than n power of 2 concurrent tasks. Makin kecil task, makin sikit pula parallel tu kan, kadang-kadang lah. Okay, and then another limitation is about the communication. Concurrent tasks may also have to exchange data with other tasks. Okay, this result is in communication overhead. Sebab apa? They depends to each other. Each task depends on another task. So this is called as communication overhead. They need to communicate with each other because they want to exchange the data. So this is actually the trade-off lah between the granularity of decomposition and associated overhead. Often determines performance bound. Sometimes is actually no need lah to decompose the problem into so many tasks. Decompose into 2, 3 or 5 at least lah. Okay, tak payah nak sampai 10, 7 ke apa semua Sebab apa? It's require, that will increase the time and also the communication overhead lah. Sebab it deals with data exchange ni Okay. Alright, so just now that we calculate the CPM and so on tu, that one is task dependency graph. We have another one, it is called as task interaction graph. So the difference between dependency dengan interaction ni dia represent the data dependency between the nodes. Okay, so subtasks generally exchange data with others in a decomposition. Yes, sometimes they need to exchange data between each other. Okay, so the graph of task nodes and their interaction is referred as interaction. So we need to represent the 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 exchanging data tu in terms of graph lah. Okay. So note that task interaction graph represent data dependency, whereas task dependency graph represent control dependency. So ada dua jenis graph. Dependency yang just now tu they represent control. Okay, we want to look at which task control the data. In task interaction graph, we want to look at the data itself. Okay, how it depends with each other. Okay, so how to draw or design the task interaction graph ni? So let's look at the example. We still discuss about the dense matrix just now. Okay, so you need to know how to design or how to transform this matrix to become task interaction graph. Okay, so kita tengok betul-betul. Kalau you tak nampak, media besarkan sikit jap. Okay, so senang je sebenarnya nak transform. Okay, you all tengok So in this matrix A, we have task 0 and until task 11. So when you read the matrix, okay, you know that task 0 and 11. So we need to draw or we need to prepare 11 nodes of the graph lah. So kalau you all tengok kat sini dia buat bentuk titik je. Tak kisah you nak buat bulat ke apa ke, janji you buat node lah. So we have 0 node, node 0 until node 11 here. Okay, so how to create the edge, how to write the edge, draw the edge. So look at the task 0 first. Task 0, dia ada interaction between node 0 itself, node 1, node 4 and node 8. So, kita tengok dekat graph ni, 0 has link with node 0, tak payahlah buat kan. Node 4, node, what else? Node 8. 8 and also 1. Tu namanya interaction. So, kalau you still tak faham lagi, so move to task 1. Task 1, dia ada interaction between task 0, 1, 2, 5 and 6. Okay, mana 1? Yang ni 1 tadi, dia ada dengan 0, dengan diri dia sendiri, dengan 2, 5 and also 6. Gitu. Boleh you all? Okay kan? So let's say kalau soalan minta, you all boleh transfer ke sini. And satu lagi, tak semua orang dapat pattern yang sama macam dalam jawapan ni contohlah. So each of you will have your own pattern of task interaction graph based on the given matrix. Okay? Alright. Task interaction graph, granularity and communication. So in general, the granularity of a decomposition is final. The associated overhead, okay, and then increase lah, okay. So for example, consider the matrix vector just now, okay. Assume that each node takes unit time to process and each interaction causes an overhead of the unit time. So kalau you boleh tengok tadi interaction ni, you can imagine each of the node has how many interaction between the other nodes. Daripada situ kita nampak lah, okay, whether it has communication overhead or not. Okay. So next one, we move on to the processes and mapping. Okay, so it said that in general, the number of tasks in a decomposition exceed the number of processing element available. Okay, and then for this reason, a parallel algorithm must also provide a mapping of tasks to process. Kena buat mapping. Kenapa? In general, generally, number of tasks selalunya exceed the number of processing element. Task lagi banyak daripada elemen yang kita nak process. Okay. So that's why we need to do a mapping. Alright. So processes and mapping, appropriate mapping of tasks to processes is critical to the parallel performance of an algorithm. Daripada situ kita nampak, bila kita buat mapping, kita nampaklah which task is not has the communication with other tasks, which task is independent or dependent and so on. So mappings are determined by both the task dependency and task interaction graph. So how to make the mapping? So we can know by drawing the task dependency and also task interaction graph yang kita dah belajar tadi. So task dependency graph, okay, you can use this graph to ensure that work is equally spread across all processing at any point. Sebab kita nampak node tu kan, dia depends to node yang mana kan. So when you implement task dependency graph, actually you will make this process minimum idling. You can reduce the idle time and also you can optimize the load balance. You can balance the task between each node. Okay, and then you can balance the data itself that need to be execute by the task that you have decomposed. So another one is task interaction graph. That so it is used to make sure that the processes need minimum interaction with other processes or not. So you can reduce the communication by looking at the task interaction graph. So then you can do the mapping. Okay. So an appropriate mapping, actually when you do the mapping actually must minimize the parallel execution time. Kalau you buat mapping tapi tak minimize, baik tak payah kan. So there are several way to minimize the parallel execution time. Okay, so the first one, bila nak buat mapping, you kena buat mapping independent task to different processes. Okay, so number two, assigning tasks on critical paths to processes as soon as they become available. So number three, minimizing interaction between processes by mapping tasks with dense interaction to the same process. So when you want to do the mapping, you need to consider this one lah. Cari task tu independent ke tak. Okay. Lepas tu assign task on critical path. Okay, sebab dia critical, you need to complete. Okay, is the most short. It takes most shortest time to execute, and then you need to find whether each processes has small or minimum interaction with each other or not. Okay. So this criteria often conflict with each other. Yes, sometimes it will conflict lah. Kadang-kadang kita jumpa independent task tapi dia punya interaction banyak. Kan? Ataupun masa yang dia ambil lama. So we need to consider all these factors. Okay. Alright. Okay, contoh. Kalau you all tengok kat sini. Mapping task in the database query decomposition to processes. Yang macam contoh kita buat tadi tu. Okay, so this is task 3, 2 and 1. So PO, P1, P2, P3 is the processes that we need to map. Okay. So kalau you tengok lagi, mapping independent task to different processes. Task 4 is mapped to P3. Task 3 mapped to P2 and so on lah. Each processes being mapped into different tasks. And that task is independent with each other. So this mapping will arrive at by viewing the dependency graph. Maksudnya bila kita buat dependency graph tu, baru kita tahu, okay, which node is depend to each what node. Okay. So baru boleh buat mapping. Okay, then tasks within a single level are then assigned to a different process. Okay, kadang kalau ada task tu dia duduk seorang-seorang single level, so it can be assigned to different processes. So contoh kat sini guys, PO1, 2, 3 ni dia dah jalan. Tapi at level 2 tu boleh guna PO lagi. Sama juga yang ni guna PO lagi, PO lagi. Okay. Tak guna P1, P2 or P3. So this is the example of mapping. Okay. Habis dah rupanya. Okay, Madam nak stop sampai sini. Yang ni kita sambung nanti hari Selasa. So far you all faham kan on how to find the CPL, to write or draw the task dependency graph, task interaction graph, kan? Okay, any question? So far so good? Okay, Alhamdulillah. Okay, alright. So kalau macam tu, kita stop dulu untuk hari ni. Dan nanti you all jawab soalan Madam di Google Classroom related to this topic. Right? Okay. Alright. Okay. Okay, thank you all. Assalamualaikum. Thank you for participating to my class. Okay. Bye. Okay.